Seasonal, predictable, smoothing theories. It's time for time series. Time. It's simultaneously one of the scariest things out there and one of the most inspiring. Something that's human-made and also intrinsically part of nature. And many of the great decisions we make in our lives will be done in relation to time. Welcome everyone to this wonderful chapter on time series, where we're going to dive into some pretty incredible data sets. We've got climate change, retail sales, financial inflation, and AFL data. These here are some real time series graphs that I've taken from sources online. We've got the Bureau of Meteorology. We've got all the sales of furniture and related sales in the US. We have inflation data in Australia. I've got points per round in the AFL. We've got some COVID data as well. Now, it took me a long time, but I managed to get the raw data sets for each of these points, and then spending many hours have been able to recreate those graphs myself. And what does that mean? It means that when we dive into our analysis of time series in this chapter, we're going to be able to use this real-life data to draw and learn some of the wonderful things we're about to learn. So welcome everyone to today's lesson on time series data and their graphs. We're going to be looking at two key skills: the features of time series plots and how to look at a time series on your calculator. I'm going to use the chance of looking at the features to show you these wonderful data sets, and we'll see where we can get a sense of how they tell us things about the real world around us. All right, we have here the annual maximum temperature anomaly in Australia between 1910 and 2021. And if you're curious about what that means, then hold on for our next lesson. I've taken some data from weather stations around Victoria from the last 100 years, and we're going to do a deep dive into weather patterns and climate change. But here, if we ask ourselves, what are we seeing graphically? We're seeing an increasing trend. A trend is a long-term direction in a time series graph, and we can either call it increasing, or we can call it decreasing, or we can say there is no trend. In this case, we're walking to the right, we're walking up, so we're definitely increasing. This set of data is the points per round in the AFL for a period of about 10 years, i.e. every single data point is a different round, or is the total points scored. So it's sort of 18 teams, somewhere between, they're not scoring 100 points each, they're scoring a little bit less. Now, we're seeing here over time that our troughs, the bottom parts, are on average getting lower, and our peaks are getting lower, and the main section of the graph is getting lower as well. So we can see that this is overall a decreasing trend. Now, there's a few interesting things happening in this graph. We see some drops, and we see something happening over here. We'll talk about that in a few slides to come. We're now looking at seasonality, and seasonality is calendar-related movements. Movements relating to the calendar, so yearly, monthly, weekly, daily. Here we have retail sales in the US, i.e. basically the entire retail sales for furniture-related sales in the US at different points in time. They're taken every quarter. So we've got our summer sales, then we've got our, what goes after summer? Autumn, winter, spring, back to summer. And this is huge. What's this, like $10 billion? Now, we can see some seasonality here because around summertime, people seem to be buying more. We get these big jumps. And then after summer, bang, it goes down. Now, why might that be happening? It could be Christmas, it could be Thanksgiving, but definitely we're having this repeated pattern that's relating to the calendar. And whenever we have that repeated pattern relating to the calendar, we call that seasonality. We see some seasonality as well when we look at our AFL points per round data. It seems to be that every season, something is happening. We're having this drop. Is there suddenly a game every year where just the teams get really tired and they don't score as many points? Or, if you're thinking, right, you might say that's because of the bye round. There's a bye round every year, and the total points scored in that round is much less, so we have this drop. It happens to be that in this data, it doesn't actually say anything about the teams themselves. It says something about the way we've collected the data, being the total for all the teams. We have this seasonal drop that seems to be happening at the same point every year. That's another example of seasonality. And here's a definition for you if you want to put it in your notes. Now, a lot of people, when they learn seasonality, also learn this thing called cyclical, whether the data is cyclical or not. People often get very confused, and then some textbooks like to define as seasonality as within 1 year and cycle is over a longer period of time. Let me talk to you a little bit about cycles, and I'll tell you why you don't have to worry about it. Cycles is the same kind of pattern as seasonality. It's sort of something repeated, but it does happen over a longer period of time. And one of the most common cycles we talk about is the economic cycle. That yes, within 1 year, we might have summer, autumn, winter, summer, autumn, winter, summer. We might have little peaks and troughs where we have a business might do better or worse at a different time of the year. If you're selling ice cream, you'll sell more in the summer. If you're selling skis, you'll sell more in the winter. But if you're a business, you're still going to feel the bigger economic conditions, and those are the conditions that happen over a long period of time. You know, it might be that every 10 years or so we hit a recession and the economy slumps, and then we move out of the recession and the economy peaks. And that's what we're seeing in this chart over here. Expansion, recession, expansion, recession. It's not always predictable in that way, but it does go through cycles. And if we're seeing this sort of cyclical pattern in the nature of our long-term economy, we call that cyclical. But the interesting thing is that while every textbook would make you think otherwise, the word cyclical doesn't appear on our VCE study design. It only talks about seasonality. And I've actually been through about 15, 20 years worth of VCA exams, and I've never seen a single question about cyclicalness. So don't worry about the difference between cyclical and seasonality. Just learn seasonality. Cyclical is not on our course. So I wondered whether I might find some seasonality in my temperature anomaly data. We're comparing deviations from the normal, so we're not necessarily expecting seasonality. What I did is I zoomed in on a specific period of time. Here this graph is 1920 to 2020. We look at the period just around the 1990s and the early 2000s, and I'm going to look for some seasonality. So how far am I deviating from the normal? I can see we go up, and then we go down, then we go up, we go down. It looks like the seasonality, and then down, and then up, and then up, and then down, down, up, down. Don't look for seasonality where it doesn't exist. Sometimes a bit of up and down is just an irregular fluctuation. Every graph's going to have irregular fluctuations, and seasonality is going to really be very clear and consistent. We don't have seasonality here. And the same thing here, we've got the CPI inflation data from Australia. Our Reserve Bank introduced inflation targeting around 1993, and we improved our ability to control inflation then, and the Reserve Bank generally is doing a great job. Recent years saw an increase in inflation, and who knows where we extrapolate and where we go, but I've got faith that in the long term they'll bring it back down. Now in this inflation data, we do see some ups and some downs, but I can't see any regular seasonality. The little ups and downs here we can call irregular fluctuations. Irregular fluctuations are going to be found in any graph of real world data. If you have a graph with no irregular fluctuations, just a straight line, then chances are it's a bit artificially made. So expect to see them almost everywhere. All right, in our AFL data, we explained what these dips were. They were according to the buy round, but what's happening over here? Now, is that what's going on here an outlier or not? It's a bit hard to say. There's a lot of data in this graph. I'm not going to make a comment about this graph. I will make a comment about this graph. I've taken here not a data point for every round, but a data point for every year. And I've said for that year, what was the average points scored? Why did I do this? I was curious to see, has scoring dropped over time? All the commentators say, the game's not like it used to be. We're not scoring as much as we did. And this graph seems to indicate that scoring has dropped. Now, you've got to be careful with your data. There was an introduction of new teams prior to around 2012. So naturally, the data, you'd expect the total points per round to be a bit lower then when there were only 16 teams, not 18 teams. And you've really got to check your assumptions before you draw conclusions. But I digress. We're talking about this point here. Clearly, there's an outlier. If we have a point for every year, we have a certain trend going on, and then boom, down there we see a big change. What's that big change, my friends? It is 2020, when we had COVID, rounds were reduced, games were shorter, and points were lower. That's a perfect example of an outlier in our data. Let's look back at our retail sales. We're looking through our seasonal cycle. We're selling more in the summer, selling less in the winter, and we go, yay, the economy is improving. One of the questions when things change is that going to be an outlier or a structural change? And here we hit 2020, you might remember, and suddenly we see a huge drop. One quarter to the next, we've dropped our sales significantly. But then at a point in time, there was real fear about what would happen in the economy. And people see this point and they say, oh my God, is this structural change? Are we going to be like this forever for the next 2 years, for whatever? Luckily, things picked up. There was an initial scare, and even followed by the next quarter, sales had improved. In fact, a lot of people were staying at home and they wanted to buy lots of furniture. So furniture sales really went up as well. This is an example of an outlier and not a structural change. So what is a structural change? A structural change is a fundamental change, a fundamental shift in the behavior of a time series graph. Here we have a certain trend, a certain behavior, then boom, a structural change, and suddenly we're doing something else. This here is a hypothetical stock split for a hypothetical Edrolo share. Maybe one day Edrolo will list on the share market and we can open the business newspaper and see how many presenters, how many students are watching Edrolo today. What is a stock split? We'll have a summary of that on the next slide. If you'd like, have a read. Basically, this change is not talking about a change in the value of Edrolo as a company. It's just talking about a change in the nature of the share structure of a company. But if that happened, we would see this kind of structural change in the graph. One sign of a structural change is something called a discontinuity, which is this kind of sharp drop, a real significant difference, right? If we're just doing a general sort of change in trend, we're not really calling that a structural change. That's just the trend is changing. This discontinuity, that really represents structural change. All right, we've done a lot of the features of a time series, but let's remind ourselves what a time series is. A time series is a graph where the x-axis, where the explanatory variable is time. And that can represent months, years, quarters. We can be counting up 2009, 2010, 2011, or we can say 1, 2, 3 for the first year, the second year, and the third year. But whatever happens, we want that time on that x-axis. If you want to draw it on the calculator, then you would put your data in as usual. And let's say in this case, I've got my first year, my second year, my third year. As usual, we give our names to our columns, and then we would make a graph. We'll go data and stats. We add time to our x-axis. In this case, my x was time. We add our values to our y-axis, and we have our scatter plot. ClassPad people, you can do the same thing. Go to menu, spreadsheet, and put your data in. One thing to note when we are drawing a time series is that we always want to connect our data points. And that connection, that little dot to dot, helps us see the trends and patterns that go on. TI Inspire people, hover over the white space, press Control and Menu, and you press Connect Data Points. And for ClassPad friends, go to Graph and Line, and if you play around with the settings there, you'll be able to get the connected dots as well. All right, we have a summary here of all the key ideas from today, the definitions for trend, seasonality, and structural change, irregular fluctuations and outliers, and a reminder of the definition of a time series. It's got time on the explanatory axis. I'll see you next time for smoothing means. Seasonal, predictable, smoothing theories. It's time for time series. Hi everyone, welcome to today's lesson on smoothing means. I'm really excited to dive together into some of the wonderful data we're going to look at today. Data from weather stations around Victoria. We're going to look at climate change, and we're going to look at changes to weather over the time. Now, I have here an official graph from the Australian Bureau of Meteorology. Meteorologists are some of the best mathematicians around the world, and if you read a bit about the background of these graphs, you'll see some pretty incredible statistical techniques they've done to show us some of the data they have today. But this graph is really a summary after a long process. There's been some averages that was taken. There's a look at the international standard between 1960s and 1990s, really some intense mathematical work. And I'd love to take the raw data together and see what conclusions we can come to ourselves using the techniques we're learning in general maths. So that we shall do. There are around Australia around 112 weather stations under the ACORN-SAT system, the Australian Climate Observations Reference Network for Surface Air Temperature. And I've taken two stations, one from Wilson's Prom, another one from Sale. I'm not sure if you've ever been to this beautiful part of Victoria, but tucked away in a little corner is one of the most wondrous places I've been to in my life. And at the very tip of that corner is a lighthouse. And in that lighthouse, for the past 100 years, someone has been recording the temperature. 100 years ago, they would have been there with a pen and paper writing it down. And more recently, I'm sure it's been automated. We got the data. We put it on the graph, and we have nothing from it. There's so many data points here. There were 40,000 data points that I couldn't possibly draw any kind of conclusion. So then we thought, well, how about we use some general maths techniques? What about a smoothing mean? Now, we're going to learn today the smoothing mean, 3 mean, 4 mean, 5 mean, 2 mean. Here, there was so much density of data, I used a 700-point smoothing mean, took the average of all the surrounding points, and suddenly we got something that looked a little bit clearer. What's this telling me? I need to zoom in. So we zoom in, and we start to see something quite interesting. The smoothing mean temperature from Wilson's Prom about 100 years ago was around about 16.25 degrees. And in more recent times, we're up to about 17.25. And I thought, is that significant? Is that significant? The Bureau of Meteorology graph had something about 2 degrees. But actually that Bureau of Meteorology graph is about anomalies. It's looking for something different. If you do some research online, you'll see that the general consensus is that the Earth has warmed by about 1 degree since industrial times. And the majority of the warming has happened since about 1975, i.e. this. In other words, the exact things that are agreed in climate science today is seen from the raw data of the Wilson's Prom Lighthouse that you can easily find and scrape online. I've never done an exploration like this before, and I was very excited. I mean, it means significant things for the world, but it was really curious to see. The conversations are around, can we limit to 1.5? Can we limit to 2 degrees? And that's sort of where the world is going. And I thought, well, this worked for Wilson's Prom. Let me check the same thing for sail. And if you look at sail, you get the same things as well. So this is the power of moving means. Let's try it today and see what we can find. We're looking at the smoothing for the movement. We're going to do a 3-point, a 5-point, a 2-point with centering, and a 4-point with centering. Notice that the centering happens when the numbers are even, and when they're odd, we don't need centering. All right, a moving mean is all about taking a data point and replacing it with an average. And by doing this, we get to smooth our data and see some of the underlying trends. Let's do an example. Let's say I wanted to find the 3-point moving mean for 2012. Well, 3-point means I'm going to take 3 points. The 3 surrounding data points, 19.7, 19.9, 20.5. If we divide that by 3, we get 20. That would be the new smooth data point. And we can do this for every single data point, right? If we take these 3, we'll get this one. If we take these 3, we'll get this one. And if we go through every possible option of a group of 3 data points, we'll get all these new smoothed values. And we'd expect them to be less noisy. There's less ups and downs because the average is going to smooth things out. That's the formula for how to do it, right? If we want to replace the 4th point, we'll take the average of the 3rd, 4th, and 5th points. A little note is we're not going to have averages or 3-point smoothing means for the first and the last point of the data set, because if you want to replace 2011, you would have to take the one above, the one there, and the one below, and we don't have the one above, so we end up getting no value for that one, and by the same principle, we would have no 3-point smoothing mean for the last point as well. All right, what if you're asked to do a 5-point smoothing mean? Well, just like the name indicates, we would take the 5 neighboring points, and the point we want would still be right there in the middle. Let's say we want to do the 5-point smoothing mean for 2005. So I need 5 surrounding points, and because 5 is an odd number, just like 3 was an odd number, it means that the point we're replacing is going to be part of our calculations. So how do we do this? We'll go 20.3, 19.7, add them all up, divide them by the number of points, i.e. we're going to take the average, and we get 20.3. So we would replace the point 2005 with a point 20.3, i.e. if there was a graph, previously on the graph, the point was 20.7, but that could be a bit of a fluctuating point. By now taking the average of the surrounding points, we get to replace that with 20.3. That is the smoothed point. It's balanced out by all of its neighbors. And if you do that for every point, you can get a 5-point smoothing mean for every point in your data set, except for the first 2 and the last 2. Can you think about why we wouldn't get a 5-point smoothing mean for those? Here's a summary of the formula. If we want to replace the 4th point, we'll take all of these points and divide them by 5. We're not going to get a 5-point smoothing mean for this one, this one, this one, or this one. And what's the reason? Because if I want to replace this point over here, I would take these points, and I'm missing someone there. All right, we're now in the realm of an even point smoothing mean, i.e. 2-point or 4-point. And because this number is even, we're going to have to do something called centering. Let's say we want to replace the point for 1993, i.e. we're going to replace this one. The question we have is, should we take these 2 points or these 2 points? And the answer is that we will have to do both. There's no reason why we should bias towards 92 or towards 94. So this is how it would look. The question is, which one should we choose? Should we go with the average of these 2 or should we go with the average of these 2? And of course, the answer is we don't want to bias towards one or the other. So let's take the average of both. And we get 19.6. Now, why do we do this? If we are choosing 2 points rather than, say, 5, we're saying, I don't want to smooth too much. I want to only consider my nearest neighbors. When there's an even number, we don't know which group to choose, so we'll consider both me and the one before me and the one after me. We'll take those averages, and then we'll average those. So we can see that whenever we have this idea called centering, we've got an extra step involved. We're taking the average of the averages. And the reason for that is we don't want to bias before, we don't want to bias after. We still want a number that connects to my original score. And so by centering the original means, we get back to the position that is unbiased above or below. And this is a formula that can summarize it for you. If you want to replace your fourth data point, then you take the average of the third and the fourth, the average of the fourth and the fifth, and then you would average those two together. And just like with 3-point smoothing mean, we're not going to get any smooth values for the first and for the last data point, and I'll leave you to think about why that might be the case. All right, what about 4-point moving mean with centering? I reckon that you could get this yourself without me explaining. What do we want to do? We want to take the average using just 4 data points. Because this is an even number, we might have to center. Let's do an example. Let's say we want to replace the value of 1987. Well, I would want to take 4 points surrounding this data. But I don't know whether I should take these ones or these ones. If you look at the 2 boxes that I've drawn around my point that I'm replacing, you'll notice that the point I replace is sitting symmetrically inside it. And that's really important because if we're replacing this point, we don't want to bias above, we don't want to bias below. And in fact, for 4-point moving mean with centering, how many points are we using in total? We're just using 5. Because for the first average, it's sort of the 2 above and the 1 below. And then for the second average, it's the 1 above and the 2 below. And in total, that's only 5 points. Does that make sense? The average of the first 4 data points is 19.575. And the average of the second set of data points gives us 19.625. Now, we know that the first average is biased a little bit earlier in the years, and the second average is biased a little bit later in the years. If we average both of those together, equals 19.6. And that's the number we would use to replace our data point for 1987. It happens to be that in this case, it's exactly the same as the original, but that's a pure coincidence. All right, and here's a summary of that formula. If we're replacing the 4th point, we take an average of 4 points. Originally, our point is let's say we're replacing this one. Originally, our point is the 3rd in the sequence. And then we do another average where our point is the 2nd in the sequence, i.e. that set of numbers there. You can see that this point, the first time it's the 3rd in the sequence, the second time it's the 2nd in the sequence. Then we have 2 numbers, and we average those, and that is our 4-point moving mean with centering. Notice that when we center, we're always just taking the average of 2 numbers, so it doesn't matter that it's 4 on the top, it's always going to be a 2 on the bottom. And there are some certain points that we can't find the smoothing means for. In this case, it's going to be the first 2 and the last 2. All right, here's a key summary of all the ideas from today. We've got our 3-point and our 5-point, they're just straight averages. When you're doing a moving mean with an even number of points, we want to put in the centering as well. So we'll take an average of the surrounding points, and then to make sure we're not biasing in one direction or the other, we average those averages, and it gives us the new point that we replace our old data with. All right, that's it for smoothing means. Next time, I'll see you for smoothing medians, which you'll find is a little bit more fun. Seasonal, predictable, smoothing theories. It's time for time series. Hi everyone and welcome to today's lesson on using smoothing medians. Why do we smooth data? It helps us understand and see trends that exist within the fluctuations. Sometimes we have lots of fluctuations in the data and we want to know what's the overall trend, and smoothing can help us get there. If we go into the land of big data, smoothing can be really, really powerful. I've been working for the last few years in a company that's doing some machine learning. And one of the tasks that you do before you build a machine learning model is you want to explore your data. And I came across data that looked very much like this. Now, I can't tell you what we were actually looking at because then I would lose my job. So let's imagine that I was trying to predict the number of birds that would appear in trees. I came across this wonderful fact where I was comparing it to how many apples had grown in the tree. And I get this data set and I say that there's just a whole bunch of random data. Sometimes you have lots of apples, sometimes you have lots of birds, sometimes the other way around. And then my boss said, hang on, Tal, try and do a smoothing median. What happens if you take the median of a bunch of points and you smooth it out? Because why did he say that? What was the genius behind his thinking? Because I can't tell where all my data is. Perhaps there's lots and lots of data here and not much data here, but because there are so many points, I can't see what's going on. So I did as the boss said, and we found something like this. Suddenly, we took the smoothing median and we saw there was a trend. Actually, there were lots of data points here, and then here, and then here, and there was a really big pattern. We found if we wanted more parrots in the trees, we could just get more apples. And that decision will potentially lead to a decision that might change the flow of a few $1 million. So my boss was a bit of a boss that day. So let's have a look. Smoothing with the moving today medians. We'll look at 3 median smoothing, we'll look at 5 median smoothing. Unlike the moving means, we're only using odd numbers and it's nice and quick and easy to do. Well, let's take us back a bunch of years to the time between 2020 and 2021. And we're going to move across the world to a land called England. Back in those days, England was going through a pretty hectic time with COVID, and cases were climbing up until about 70,000 cases a day. Around the switch to 2021, it was sort of one of those phases. There was a whole bunch of factors, lockdowns, release of lockdowns, vaccines were coming into play too. We saw a drop. When we were back in those days, we had lots of fluctuations in our data. And if you remember back in Victoria, we were told that we're going to look at the 7-day moving mean. That's very much like what we looked at last lesson. We took the average of a bunch of days and we said, we're not going to just care if one day is higher or lower. We're going to care if the average as a whole is moving up or moving down. And we'll use that to help us make decisions. So that's what we're going to look at today. We're going to look at some COVID data. We're not going to look at the moving mean. We're going to look at the moving median. And we'll see if we can plot these 3 median and 5 median with the data points before us. To get the moving medians, we need to see the original data points. So we take our time series, we strip away those dot-to-dot lines that connect the points, and then we dive in. If you wanted the moving median of 5 points here, you would be looking at 5 surrounding points, and you would say, what's the median of those points? Just like we found the mean in our last lesson. So let's look perhaps around this time when things are changing, around sort of Christmas of 2020, and find some medians there. All right, we're in December of 2020, and when there's a bit of fluctuation, some days are higher and some days are lower. How can we smooth this out to get a sense of the general trend? We're going to take a 3 median smoothing to do it. That means I'm only going to ever consider 3 points. I'm going to replace the middle point, okay? So I'm saying I want to find a new point for the 19th of December. The way that I do it is I want to take the median value, the median number of cases for those 3 points in the region. So I say, listen, I've got 3 options for the number of cases. Which one is in the middle? We can see pretty clearly that this point over here is the one in the middle. It's the median value. So that's going to be my new value for the 19th of December. The key idea here is that when you're considering the median, you don't think about left and right. You only think about up and down. The left and right helps us determine which point are we replacing, what date are we trying to smooth for. And once we've fixed that point, we just consider up and down. I'll show you what I mean. Let's say we're trying to replace the 20th of December. So we're looking at these 3 points here. We fix ourselves on the 20th of December, and now we just consider up and down. All right, I'm going from the bottom to the top, and I'm saying, what is the middle Y value? What's the middle number of cases? We can see it's the middle point here, so we replace it with this value. I'll do it one more time. Let's say we want to replace 21st of December. So we're going to fix ourselves here. We're saying I'm going to replace the 21st, and now I just consider up and down. Which one is in the middle? If I go up and down, I want the one that has one above it and one below it. We can see pretty clearly it's this one. So that's the value we use to replace the 21st of December. So I've drawn 3 points for you. I want you to consider what would happen if you went further along. If I gave you these 3 points and said replace the 22nd, which one would you choose? If I gave you these 3 points and said replace the 23rd, what would you choose? And just to give you a different kind of example, what if I gave you these 3 points and said replace the 25th? Which point would you choose? So here's a key summary of how to do it. One technique that people like to do is they say draw a line through the point you're trying to replace. Now find the median height, which one has one above and one below, and draw a line through that. And wherever your lines intersect, that's where your new point will be. So this is the final graph of the 3 median points for all of these dates at that time in December. Notice that when we draw them, we connect them afterwards, so we can also see the trend there. And we can see there wasn't much change. There was, even if we smoothed it out, we had a bit of a rise, a bit of a fall. There's not a significant underlying trend. And if we do it to all the data points across that period of time, we can see a little bit more clearly the general trend. There's still a bit of a regular fluctuation up and down, maybe the way that they collected their data, or maybe there was more or less testing on the weekends that caused perhaps some seasonality, or perhaps it's just irregular fluctuations. In this case, the overall trend seems to be more powerful, and we can see that even in the original data as well. For 5 median smoothing, we're going to take the same principle, but we'll just be taking the median of 5 points rather than 3. And that's going to result in our final smoothing, our final moving median line being less volatile and with less fluctuations than our original data, and even with less fluctuations, they're now 3 median smoothing line. You can see that here, if we do the same smoothing but using 5 points, we're going to get more of a flat line, and by itself, that little piece of point, that little piece of graph doesn't tell us too much. But if we look at it and do it for all of the graph, the piece that we looked at was probably sitting around here, we can start to see a bit of a general trend. We're cutting out the big ups and downs, and we're getting the general overall trend. We're sort of more clearly seeing the rise and the fall. And I agree with you that here you can probably tell it from the original data as well. But like I showed you at the beginning of the lesson, when you have lots and lots of data, some of these techniques become really, really powerful. So let's practice the 5 median smoothing. Same principle, but just 5 points. So can I take a smooth value for the 19th of December? No, because I don't have 5 points surrounding it such that this is the middle point. So for example, I don't want to take these 5 points because it's not the middle one. I would need to take these 5 points. I would need another point over here which doesn't exist. So I can't take the smooth median value for my first 2 points. The first one I can use is this one. Why is that? Because I can draw a nice box around the 5 points. So we're going to fix our point at the 20th of December. And we're going to replace this point. Remember, once we fix it horizontally, we no longer think about the horizontal, we just think about the vertical. So I want to now go up and down and find the point that's in the middle. What's the point that's going to be in the middle? It'll be the one that has 2 above and 2 below. And you can pretty clearly see it's going to be that one, right? It's the median point for the number of cases. So we bring that across, and it's our new point over there. All right, what about the 21st of December? Let's surround 5 points. We can see the 21st of December is right in the middle. We fix that spot, and now we just think up and down. I want to find the point. That is 2 above it and 2 below it. What you could get to is you could just count 1, 2, 3. So start at the lowest, 1, 2, 3. Aha, that's the point there. Bring it across, and we have our smooth value there. Now let you have a think about what the other values might be, and we'll practice it just like the 3 one with some multiple choice questions. So just to summarize the idea, we have a nice picture over here. We fix our point here. Some people like to draw a vertical line through that point we're replacing, and then you count up 1, 2, 3, or you can count from the top down. If it's the middle, you're up to the same point. Either way, we end up at this point over here. If we draw a horizontal line through that, the intersection is going to be our new point. All right, those are the key ideas from today. 3 median and 5 median. Fix your horizontal value, and then find your middle vertical value. I'll see you next time for seasonal indices. 'Tis the season to be mathsy, tra-la-la-la-la-la-la.
Ho, ho, ho! Welcome to seasonal indices.
All right, everyone. Today's lesson and the following one are all about seasonal indices. Today, we're going to interpret seasonal indices and understand what they mean. We're going to use them to deseasonalize and re-seasonalize data. If you're looking to learn how to calculate seasonal indices, then go into the next lesson, where we go through all the techniques over there. We've seen seasonality before. We've seen it in our data when things fluctuate up and down with a regular pattern according to the calendar. The question is, how do we tackle and interpret and predict data that follows that form? And that's where seasonal adjustments and seasonal indices come into play. So there are 4 key skills today. We'll look at the key terminology surrounding seasonal indices. I know that this is often a very difficult topic for students, and we're gonna wrap our heads around it. We'll interpret seasonal indices. We'll look at deseasonalizing data and re-seasonalizing data. Now, if you've come looking for that really tough skill, that multiple choice question where you're given this seasonal index of 1.25 and it turns out to be 80% rather than 25%, you're like, what's going on? That's in the multiple choice section over here. We'll look at a tough question there. If you come here looking to calculate seasonal indices across a few years or from the raw data, go to the next lesson. We'll do it there. All right, before we get into calculations and formulas, let's get an understanding of what we're looking at. And I want these graphs to sort of stick in your mind whenever you're calculating seasonal indices or using them to find data. I have here the furniture and furnishing sales in all of the USA across time. So we're talking billions of dollars here. And we saw in previous lessons that this data is seasonal. In the summer, we have lots of sales. People are out buying furniture, perhaps around Christmas, perhaps around New Year's, and then there's a drop at other points of the year. If you were trying to fit a regression line through this data, you'd run into lots of issues, and the regression line wouldn't be so successful because it would get confused by this constant rise and fall of data points. So what we do is we deseasonalize data. The word deseasonalize means take the seasonality out. And that's what we have over here. And in fact, the Central Bureau of Statistics in the USA publishes both of these graphs, the seasonalized ones for those who want to understand the actual raw data, and the deseasonalized ones for those who are trying to see the general trends and to make predictions perhaps with some statistical tools. So whenever we look at our data, we're going to be talking about two types: the actual data, which is here in blue, and the deseasonalized data, which is not the actual value, but it's the value that's been adjusted to remove that seasonality component. All right, we know the difference between our actual data and our deseasonalized data. The question is, how do we go from one to the other? How is this red line calculated? And the tool that we use to do it is something called the seasonal index. In our next lesson, we're going to look at all the different ways to calculate the seasonal index. Today, we're going to focus on just interpreting what it means and how to use it. The way to help us get there is to sort of say, our actual data is this. It's our data with all its trials and tribulations of seasonality involved. And the red data is our deseasonalized. And the red data can also be thought of as the average. What's happening on average? Yes, I know that in summer I might sell more, in winter I might sell less, but on average, what are my sales doing? That's another way to interpret deseasonalized data. So this seasonal index comes along and it says, I'm going to tell you in the fourth quarter how much above average or below average our actual sales are. So here's the example. 1.2 means that in the fourth quarter, our sales are actually 20% above average. If you had a seasonal index of 1.05, that's a number bigger than 1, so that tells us we are 5% above average. And if we are 0.65, that's a number below 1, so we're actually going to be 35% below average. Now, I think you can see pretty clearly what's going on. If you want a nice formula to get this, you would do 1 minus that seasonal index, and you would times that by 100. And if you do that for each of these seasonal indices, you'll get those numbers, 25 and 35, that we've just spoken about. And that's the idea summarized over here. If you had a seasonal index of 1, you would neither be above or below average. All right, with that understanding, we can draw out a formula to work out what's going on. If our seasonal index was 1.2, then we'd be saying, all right, take your deseasonalized figure, your average value, and let's say you're here. If I times that number by 1.2, I'm going to jump up to get my actual figure. What if my seasonal index was 0.4? Well, then I might be looking at this point over here, right? That's my deseasonalized value. It's my average value. If I times that number by 0.4, we get down to our actual value below. That actual value that has all the seasonality inside it. So that's what this formula says. It says to get the actual value, multiply your deseasonalized figure with your seasonal index. And if you want to do a bit of algebra, you can move this seasonal index. You can divide by the seasonal index on both sides of the equation. You'll get a formula for that deseasonalized, that average figure. It's the actual figure divided by the seasonal index. Let's use these formulas now to calculate either the deseasonalized or the actual figure in some different contexts. All right, in the previous questions, we were using this formula. The deseasonalized figure equals the actual figure divided by the seasonal index. It's the same formula as this, it was just the one that had been moved around. We're now going to practice using this one. So let's just understand what we're doing because it'll help with the terminology. Previously, we were saying, I know the actual figure. Can you tell me the deseasonalized figure? That was what this formula gave us. This formula is going the other way. It's saying, I know the deseasonalized figure. Can you tell me what the actual figure is? Write this down and use it for the next few examples. All right, those are the key ideas from today. I really recommend to just keep this image in your mind. I think it's really useful. Our fluctuating values, they're our actual values. Our deseasonalized values, they're the ones that have had the seasonality stripped away from them. They're kind of like what's happening on average. And I've also put here a few examples for all these kinds of common questions you might face in this category of seasonal indices. If you have questions around how do I find seasonal indices, how do I calculate them, then that's going to be in the next lesson. But for any other kind of question, you'll get your answer from this slide over here. I'll see you next time for part 2. Seasonal predictable smoothing theories. It's time for time series. In our last lesson, we gave seasons greetings when we spoke about seasonality. And I thought this would be a great opportunity to celebrate multicultural Australia. I have here some data from the Australian Bureau of Statistics back in 2021 that showed then we had about 44% Christianity in this country, almost 40% of people had secular beliefs, and then we have a range of other wonderful religions through here as well. In the other religions category, that includes such religions as Baha'i and Indigenous Australians' traditional religions. We speak about the rise and fall of money over time with our time series. We can also speak about the rise and fall of celebrations during the year. Whatever season it is for you and whatever time of year you're watching this, season's greetings Eid Mubarak, Shib Diwali, and Chag Sameach. So today we're on part 2 of our journey into seasonal indices. Today we're going to look at 3 key skills, and they all surround calculating the seasonal index. If you're looking to how to find deseasonalized data, how to account for seasonality, how to find the actual figure, go to our last lesson and you'll learn it all there. You'll also learn how to interpret seasonal indices as well. If you're looking at how to find the seasonal index, been given some data, I need to calculate it. I've been given a list, I need to find it. If you want to find that seasonal index, then this is the lesson for you. So just as a reminder, we had this wonderful data set of furniture and furnishing sales in the US over time. And we saw it was seasonal. In the summer, we sell more, and then in the season immediately following, we sell less. And that pattern is repeated year in and year out. The blue is our actual data, and the red is our deseasonalized data. It's kind of like what's happening on average if we take this seasonality out of the equation. We said that the seasonal index is what you multiply the deseasonalized data by to get the actual figure. So this red is our deseasonalized data. It's what's happening on average. If we multiply it by, 1.2, we'll get to our actual data. Or over here, if we take our deseasonalized data and we multiply it by 0.7, we'll take 70% of it, we'll get down to our actual data over there. Hopefully that's a bit of an overview and a bit of a reminder of the difference between these terms. We're going to dive in today and really focus on this seasonal index here. And one of the ways we'll find it is by rearranging this formula. So if I move the deseasonalized figure to the other side, I'll get that the actual figure divided by the deseasonalized figure is one way to give me the seasonal index. And that's summarized over here. If we want to find this number, we'll take an actual, we'll divide it by a deseasonalized, and that's going to be our first method for finding the seasonal index. Another way to find the seasonal index is to use the idea that our seasonal indices will average to 1. Why is that the case? If I have sometimes high and sometimes low and sometimes high and sometimes low, when I deseasonalize that data, I get what's happening on average. And that means that my seasonal indices across my entire time period have to balance each other out, right? If sometimes I'm above average and sometimes I'm below average, my average has to be right in the middle. My average has to be at 1. And that means that the average of all seasonal indices is 1. And that leads us to the second technique for finding seasonal indices. I just need to find out what's missing over here. I'm going to get you to do that yourselves with the next question. All right, all the methods up until now are kind of cheat methods. They're ways of calculating the seasonal index if the seasonal indices have already been calculated. Yeah, like we knew the other seasonal indices in the most recent example. And in the very first example, we knew what the actual and the deseasonalized values were. If you have the deseasonalized values there already, then the seasonal indices have to have already been calculated. We kind of worked backwards to find out what they were. We're going to find out how do people actually do the deseasonalization in the first place. How do you take a set of data and from the actual raw data, find the seasonal indices? The first stage we're going to do is calculating it from just one cycle, like 1 year's worth of data. And then for more complicated examples, we'll do it for 2 cycles, like calculating it over the course of 2 years. Let's think about what the seasonal index is. It tells us how much the actual data is above or below average. So clearly, to find this seasonal index, we're going to need to find the average data. And you can see that over here, that's going to be our first step. Calculate the average sales across the entire year. And then the second step kind of follows logically. Well, if I know the average sales, I can check how much is my actual data above or below the average. All right, let's actually solve this question. The first step is to find the average for the entire year. So step 1, find the average. How do we do that? We'll add up all of our numbers and we'll divide them by 4. We get that the average sales in this year was $1,450. Now, we want to find the seasonal indices. And the way that we'll do that is we'll take our quarterly sales and we'll divide it by the average. So for Q1, we would take 1,250 and we would divide it by the average. And you can see already from this that our seasonal index is going to be smaller than 1. 1,250 is below 1,450. If we do that division, we get 0.86, i.e. our actual sales in this quarter are 14% below what's happening on the average. You can do the same thing for Q2, right? 1,460. What do you expect this one to be? Yeah, it's going to be a little bit above. It's about 1% above the average Q3 and Q4. So if we wanted to sort of summarize our seasonal indices, we could do it like this. We could say that's our quarter, that's our seasonal index. For the first quarter, second quarter, third, and fourth, we have each of these numbers. If you've done it correctly, your seasonal indices should all add up to give you 4. If you had 12 months, they'll give you 12. In this case, there's 4 quarters, so we should get 4, and we do. Hopefully this example gives you a clearer and easier understanding of what a seasonal index is. It's just telling us how much the sales are above or below average. Hopefully this example here has given you an understanding of how seasonal indices work. They're just telling us this actual piece of data. Is it above average or is it below average? And by how much? If you understand what we did just here, you've gone a long way to understanding this weird and wonderful process of deseasonalizing data. All right, what we've just done is we've calculated the seasonal index by looking at just 1 year. But in practice, when we work with data in the real world, we're not just looking at 1 year, we're looking over a long period of time. We might be looking over 10 years, and we've seen in those 10 years, yep, summer is bigger, winter is smaller. Summer is bigger, winter is smaller. I can see a consistent pattern, and I ask, on average, how much is summer bigger? How much is winter smaller? I don't care so much about what happens in the 1 year, I care about what happens over the course of many years. And that means that we want a seasonal index that's going to summarize that behavior of summer over the entire decade. I don't want 10 different seasonal indices for summer for each of the 10 different years. I want one single one. So that means that when we calculate seasonal indices, we want to try and summarize them together, i.e. we can do what we just did in our previous example. We can find a seasonal index for Q1, Q2, Q3, Q4, and we can do that for 2023 as well. But if we want one final seasonal index that will really summarize the behavior of summer or the behavior of the fourth quarter in one number, then I'm going to want to find the average of each of them. And that's described in this process over here. Let's go forward and practice it so you can do the skill yourself. All right, we want to find the seasonal index for the second quarter of this data. The way that we're going to do it is we're going to first find the seasonal index for Q2 in 2022. Then we'll find the seasonal index for Q2 in 2023, and then we'll average them together. To find the seasonal index for Q2 2022, I need to know the average of 2022. We'll do that. We'll go 840, all these 4 numbers, add them together, and divide them by 4. So that means that the seasonal index for Q2 in 2022 is going to be the sales, which was $920, divided by 780. It's 1.18. So if I just had one row of data, that would be my final answer. But I've got 2 rows of data. I want to not just know what happened in 2022, I want to know what happened in 2023 as well, and I want to summarize both of that information together. So let's find the answer for 2023. The average sales in 2023 was $682.50, and the seasonal index was 1.17. All right, we have our seasonal index for the second quarter in 2022, and we have it for the second quarter in 2023. The way we find the seasonal index for the second quarter across all our data set is we average the ones that we have already. So we're going to take our 1.18 from 2022, but I want to make sure I use all the decimal places. And in fact, the decimal places there was 1.79487. There was a whole bunch. I'm going to use that entire number, and I'm going to do the same thing with the second one. It was 1.172161. I use all those numbers, and when I average those two together, I get 1.18 as my final answer. Boom. Seasonal index for the second quarter. All right, those are the key ideas for seasonal indices. We can use the formula if we know the actual and the deseasonalized figure. If we have all the other seasonal indices, we can find out what's missing by knowing the average for quarters should be 4, or the average for months should be 12. If we have one cycle of data, we just compare the sales to the average for the entire data set. And if we have 2 cycles of data, like 2 years, we'll find the seasonal indices for each of them and then average the seasonal indices for the required quarter or month or season. Now, these skills are considered challenging. Lots of students struggle with them. If you can practice and really get your head around them, then you're going a long way to really acing your subject, but also hopefully building your understanding of seasonality and deseasonalization as well. I'll see you next time. We'll look at how we can fit regression analysis in with the idea of seasonality. Seasonal, predictable, smoothing theories. It's time for time series. Gather round, my people, and hear my prediction. After summer, there will be autumn, then winter,
And following that, spring.
We've learned two powerful skills in our course so far: how to make predictions using linear regression, and how to deseasonalize data and to account for seasonality. What's going to happen if we bring the two together? That's what we'll look at in today's lesson. There'll be two key skills: how do we fit a trend line to a time series, and how do we make predictions with reseasonalizing the data. Let's think about what would happen if we try to fit a regression line to seasonal data. All right, so our blue points here, they're our actual sales, and they've got some seasonality involved in them. Right? Around the end December time, we look to have more sales. If we tried to fit a regression line through this, our line is probably going to be pulled up by that seasonality. And if we did this over an extended period of time, we can see that if we tried to get some least squares regression happening here, we wouldn't quite do it so accurately. The squares would be too big. Our model isn't going to work. Our model works really nicely when our data is linear and when it has a nice consistent pattern. So what we do is we plan something else instead. We say, let's deseasonalize the data and let's put a line through the deseasonalized data. It'll look something like this. That's going to be a really nice line that can predict things really well. And then we say, well, if we remembered how to deseasonalize the data, once we make a prediction on this green regression line, we can use those seasonal indices to get back to our actual sales. And the fact is that if we do it through this method, we're going to get better predictions than if we did otherwise, because our regression line is going to be a better regression line, and we can then bring the seasonality back in later using our seasonal indices. Let's give a go and practice how to do this. The very first thing that we do is that we fit a regression line to the deseasonalized data. You'll notice here that my data is deseasonalized, so it's not going to have all the seasonal fluctuations. It's going to be nice and consistent, and we'll get a really good regression line. Let's do that now. I want to show you a little bit about how we play with these months when we put them into the explanatory variable. All right, we've put our values in. Notice that for the explanatory variable, I've given the numbers 1 down to 14 because I can't really put January, February, and March in. And we're going to have to remember that going forward, that the number 1 means the January month, and the number 2 means the February month. We'll give it a name, M for months, and for our response variable, we'll call it the deseasonalized DS sales. Another interesting thing to note is that these are all counted in millions of dollars. So this is actually $8,310 million. It's $8 billion. To draw the regression line, we do as we usually do, add our months to here, and our deseasonalized values to there. We can see we're not seeing a lot of seasonality. It seems to have been brought down to the mean. An analysis with regression, and we show our linear line. I'll use the same name given to me in the question, so my explanatory variable here is date. Classified people, you know what to do. Menu, spreadsheet, put your data in, calc, regression, linear regression. So fitting a trend line to time series data isn't so different to fitting it to any kind of data. If our data had seasonality in it, very likely we'll be asked to fit it to the deseasonalized data. The other thing is that often we'll have dates which you might have to convert into numbers. So for example, if I start in January 2004 and I want to get to October 2005, well, so October is the 10th month, but it's another year away. So I'll do 10 plus 12, that'll give me 22. We've sketched our regression line through our deseasonalized data, and we get this green line over here. How do we use it to make a prediction? Well, our regression line is predicting a value for our deseasonalized figure, right? The sort of what's happening on average. And the way we get to the actual figure, or in this case, the actual prediction, is we multiply it by this seasonal index. Let's give a go at doing that now. All right, we want to make a prediction about the sales in April of 2009. We have our original deseasonalized data, which we fit a regression line through. Let's write that down. It was the deseasonalized sales equals 8330 plus a certain coefficient times the date. Okay, we're asked to predict for April 2009. We have to ask ourselves, when is it? January 2004 is the number 1 in our data. That means that April is going to be the 4th month, and we need to go another 5 years away, right? We're in 2004, we have to jump forward 5 years to get to 2009. So plus 5 times 12, that's going to be 64. That's the number we're going to put in to make the prediction for our deseasonalized sales. The deseasonalized sales will equal this times 64, and we get 11054.08. All right, that's what happens if we extend our line into the future. That's the point that it will be. But we know that this entire prediction was predicting the deseasonalized sales, right? It wasn't predicting the actual sales. So to find the connection between our deseasonalized sales and our actual sales, we need our seasonal indices. So in this question, we assume that we have them already. We can see here that the seasonal index is 0.92, which means that the actual sales are about 10% lower than average. Our prediction for the average is this prediction over here from the deseasonalized values. So to find our actual figure, we do what we always do, deseasonalized figure multiplied by the seasonal index, and we get 11054.08 times 0.92, and that gives us 10169.7536 as our actual sales. But let's make sure we remember all the parts of this question, that our sales were quoted in millions of dollars. So we need to times that by 1 million, and that will be our final number. It's about $10 billion. That's a lot of sales of couches and chairs. Let's just remind ourselves what we did there, because there was a lot going on. We want to have a picture to help remember what happened. We had our deseasonalized data, which is the red. We fit our regression line, which is the green, and we predicted out into the future. Our prediction gave us a certain number, and we said, cool, that's the prediction for the deseasonalized values. But we know that our actual values are different. In April, our actual values are a bit below the average. So we use the seasonal index to jump from here to here, and that there is our answer. Now, of course, just like when we do usual regression lines, there's a bit of a limitation in making predictions. What did we say before? That we said that in 2009, we predicted that the sales would be around $10 billion, i.e. we took the data from here between 2004 and 2005, we fit a regression line through it. We extended the line all the way to there. We made a prediction, we decreased a little bit because of seasonality to find the actual value according to the prediction, but it was totally wrong. What happened in 2009? There was, of course, the crash, and sales of furniture were significantly lower. There's always a danger in extrapolating. All right, those are the key ideas from today's lesson. We like to fit a regression line through our deseasonalized data. We can use it to make a prediction. Then we use our seasonal indices to jump back to our predicted actual figure. But if we're going and extrapolating outside of our bounds, we have to be wary because extrapolation can lead to some mistakes. That's it for Chapter 4. There's a progress check and a chapter test, topic test coming up. See you next time for Chapter 5 and 6 with financial maths.